Thank Party Gravy. That was my theme song, Rocket Man. And if you think about the lyrics, it's the science that I don't understand. It's just my job 5 days a week. So that is what we're here to do today, is to understand the science behind one of 2012's most exciting discoveries, the Higgs boson. Now tonight we're trying to do something just a little bit different, and this is something that we're trialing for what we hope is to be a larger lecture series over the next coming years here at ANU. One of the things that I realize is that ANU is a critical part of the Canberra community, but I really want to get people out from Canberra to experience essentially the intellectual side of the ANU, but make it something more than just a lecture. And so we're hoping tonight will be the beginning of something that you'll be looking forward to over the next several years, where we get some of the most exciting minds across the world to come here and tell us about what they do, but also reflect on some of the other aspects of the university, the music school, the arts school, and just the entire intellectual environment here. So this night came about from a very ill-judged moment that I had on the 27th of October, 2009. And I was talking to my old office mate, Sean Carroll, who, via Facebook, who was being very excited about the fact that the Large Hadron Collider, which you'll find out about, was back producing particles. And you can see in our Facebook conversation from the day, I say, "So Sean, I'm looking for someone to make a bet with me that the Large Hadron Collider will not discover the Higgs because it does not exist. Are you a taker? E.g., that you bet that the Higgs will be discovered." So Sean said, "You're on, what's the stakes?" Sean, I've learned, is a very smart guy. He likes to play poker sometimes in Vegas, and I should have known better about that. So there started a bet, and the bet was that if I lose, I will pony up business class airfares via frequent flyer miles for you and Jennifer, his wife, who's in the audience tonight, to come to Australia. You will be required to give a colloquium at Mount Stromlo to explain the Higgs at a Mount Stromlo colloquium, which he's going to be doing tomorrow. But I figured while he was here, we might as well get him to do something even bigger, which is to tell us about the Higgs particle. So in my case, I missed out on a very nice culinary evening in Chicago, but I was asked, well, were you upset about losing? And the answer was no. The Higgs particle is so exciting for physics. I like losing bets where I'm excited about the outcome. Now, this was not my first bet with Sean. My previous bet we made when we were graduate students together. And there we bet that we couldn't figure out how much stuff there was in the universe. By the time 2011, 20 years passed. And we were graduate students, which means we didn't have a lot of money. And so we went out and we bought a 1985 vintage port and put it in the professor we figured would still be around in 2011's office. That's most of them. And we went around, and in 2004, partially due to my own work, we did figure out how much stuff there was in the universe, something that we know to about 0.1%, and you would have seen last week with the Planck experiment, that most latest measurement. So I completely misjudged the situation. I was very pessimistic. Sean was very optimistic. And in both cases that Sean has been optimistic, he has been right. There is a lesson in that. So tonight, Sean is going to tell us about what he knows better than I do. Hopefully he'll tell you why I was wrong and he was right. And as our compare for the evening, I would like to introduce 666 presenter Adam Shirley, who most of you may not realize is not just a science junkie. He's someone with a science degree and someone who did a degree here at ANU in science communication. So, Adam, please come out. Thank you.
And Brian Schmidt talks about exciting minds being in and around our presence. I don't think there's any more that are more exciting, more well-learned and more high-achieving than Brian Schmidt himself. So it is fantastic to have Brian Schmidt along too. And he makes a bloody good drop of red, apparently, although I've never tasted it. It is rare, to be sure, to have two minds such as Professor Schmidt's and Professor Carroll's in the same room at the same time. Brian, I do probably speak for most of us, I think, when I say in the nicest possible way, we are so pleased you lost that bet. Professor Carroll will speak to us tonight about the mysterious, elusive, but oh so important Higgs boson. If it were a party guest, it would be the star celebrity that the paparazzi could never get a photo of until now. Professor Carroll is better placed than most to tell us about the wonder of Higgs. He's been studying the universe, dark energy, and the cosmos for the majority of his life. He's also been a bit of a science rock star in his time. He has regularly appeared on the History Channel, the Colbert Report, and featured on the Morgan Freeman narrated series Through the Wormhole. There'll be plenty of opportunity tonight to take advantage of having Professor Carroll here in Australia with us. After his presentation, you can ask questions, don't be shy, it is a once-in-a-lifetime opportunity. You can also tweet them through if you're Twitter inclined. My handle is Adam M. Shirley, and if you'd like to tweet a question, I think I've been told that's the way to do it. But plenty of time to ask you questions. There's a couple of microphones set up at either side, so I really encourage you to take this opportunity while you can. Let's get into it and get him to, well, partially earn that return airfare courtesy of Professor Brian Schmidt. Welcome to Professor Sean Carroll tonight.
Thank you. Is this working? Can you hear me in the back? Is it being amplified? Yes, it is. All right, very good. Well, thank you, Adam. Thank you, Brian, very much. Thank you, Brian, for continuing to make bets where I can take advantage of your pessimism. And we've promised ourselves we're going to work hard tonight to find one more bet to do. And so who knows who will be traveling where. I promise that if I lose a bet, Brian can take a very slow tugboat across the ocean to Los Angeles to come visit us. So why are we here tonight? Well, in July of last year, I was fortunate enough to spend my time in Geneva, Switzerland, at CERN, the European Particle Accelerator Laboratory, home of the Large Hadron Collider. And what was going on American Independence Day in 2012 in Geneva? Well, there were kids parked out overnight to get good seats. And I mean, as much as you guys, were really looking forward to here tonight, I don't think there's anyone here at 2 a.m. waiting in line to get the good seats. But here we are, the night before. It's just like, a rock concert. It's a Lady Gaga concert with a lot more laptops in the audience. And what were they waiting for? It was not Lady Gaga. It was PowerPoint presentations. The next morning, 9 a.m., there were two PowerPoint presentations by Fabiola Gianotti and Joe Incandela announcing a discovery, of course, of the Higgs boson particle. And this was big news. The 20-year-old physicists were camping out overnight. The 80-year-old physicists who had helped invent the idea back in the 1960s were in the audience that night, and some of them literally broke down afterward. It was a very emotional moment. So the question that you should be asking is, what is the big deal? And I know that you are asking this question. Many people have asked me this question. Many physicists have tried to answer this question and done a very bad job of it. For example, some physicists dubbed the Higgs boson the God particle. We won't do that here in this room. You're not allowed to say those words. But it's indicative of how difficult it is to explain why the Higgs boson is really important. And so I want to take an unusual tack on trying to get there tonight, but the whole point of this talk really is to impress upon you why so many talented people devoted literally decades of their lives to looking for this elusive piece of nature. So back in the 1930s, you could forgive a working physicist if they thought that we were close to figuring it all out. In the 1930s, we'd put together quantum mechanics, we'd put together relativity, and it was the first days of particle physics. We were discovering that the universe was made of elementary particles. We thought that atoms were making up the universe, but we dug deeper. We found that atoms were made of other particles. There are electrons, which are responsible for electricity and for atomic structure. And Rutherford and others had put together the structure of the atom. There's a middle nucleus that by 1935 we knew was made of neutrons and protons. And so there were three kinds of elementary particles, 4 particles and 4 forces. It's not that much more complicated. Now, there's one complication that came along that literally a famous physicist of the time said, "Who ordered that?" It's the fact that the electron, the two quarks, and the neutrino are a family of particles, a family of 4 kinds of particles, but it's one of 3 generations in that family. So, in fact, there are 12 kinds of matter particles, as we say, or fermions. These 4, the electron, neutrino, and the up and down quarks, but also it's repeated 2 times. There is a muon, heavier cousin of the electron. There are charm and strange quarks. There's a muon version of the neutrino. And then there's a tau particle, another heavier electron, top and bottom quarks, and a tau neutrino, and nobody to this day knows why. There are ideas, of course. We have plenty of ideas. Ideas are free and cheap, but we don't know what the right answer is. Nevertheless, this is the basic picture of particle physics circa 1980 or so. Now, one of the reasons why it is difficult to go from that picture to explaining why the Higgs boson is important is because we've been lying to you when we've been showing you this picture. There's a whole field of human endeavor called particle physics. You can buy books like The Particle at the End of the Universe. You get the idea that the world is made of these things called particles. But that idea is not the whole story. It is, I might want to go so far as to say that the idea is not true. It's good enough for many, many purposes. When you're talking about these particles you see right here, the word particle is fine. But the one missing piece, the Higgs boson, you want to say, well, why do we need the Higgs boson? Then we have to admit, you know what, this particle language we've been using, it's not really the final answer. The final answer is that the world is made of fields, not particles. If you had a little bit of physics education, you might have come across this puzzle. Is matter or photons or electrons, particles or waves? And if you, even if you've had a lot of physics education, you might never have heard the answer to that question. The answer is it's waves. That's the answer. We actually know the answer. It's not a mystery. A wave, an oscillating field that fills the universe. That's what light is. That's what photons are. That's what electrons are. That's what quarks are. That's what everything is. The best understanding we have right now in 2013 of the fundamental nature of reality is that it is a set of fields. So what does that mean? Well, think of a magnet. What does a magnet do? A magnet sticks to your refrigerator. That's what magnets do. Now, lots of things stick to your refrigerator, like a piece of tape or a piece of gum would stick to your refrigerator. In Australia, you have all these sort of animal species that will stick to refrigerators and so forth. But the difference is that the gum or the gecko or whatever, they have to touch the refrigerator to stick to it. A magnet, if you hold it close, you can feel it pulling on the refrigerator before they touch. How does it know that it's close to the refrigerator and wants to be there? How does the magnet keep track of how far away from the refrigerator it is? The answer is that you can't see it, but at all times there is a magnetic field surrounding the magnet. Just like there's a gravitational field that reaches out and pulls down the laser pointer, there are these fields that fill empty space that you cannot see. The magnetic field is part of what we call the electromagnetic field, that's responsible for both electricity and magnetism. So it turns out that is the right way to think about the universe. Even the particles of matter, the electron, the quarks, the neutrinos, there are fields that are associated with them. There's an electron field, an up quark field, a muon neutrino field, and so forth. When you actually get to your second year of graduate school in physics, we finally tell you, it's not particle physics. It's field theory that really matters. So if that's true, if that story is correct, why are we talking about particles? The answer, of course, is quantum mechanics. When you take quantum mechanics and fields and add them together, you get what is called quantum field theory. So I'm very glad that Brian has brought me here to Australia to give me the opportunity to give you, over the next 6 hours, a lecture series in introductory quantum field theory so you can understand how modern physicists think. But we'll see if we can't talk really fast and get it all over with. Here's the secret of quantum mechanics, another thing they never tell you in popularizations of physics. What is the reason why quantum mechanics is so deep and difficult And the answer is, unlike pre-existing methods of physics, quantum mechanics distinguishes between what is really going on and what you see when you look at something. In classical mechanics, you have baseballs traveling on trajectories. You have the essence of the baseball is where it is. Cricket ball? What should I be using here? You have the position and the velocity, and that is absolutely well defined and absolutely measurable. In quantum mechanics, you can observe the position, you can observe the velocity, but that is not what is real when you're not looking. What is real is a wave, something that is spread out all throughout the universe that tells you the probability of seeing the baseball or the cricket ball or whatever at different positions or velocities. So a field is just something that takes on a value everywhere through the universe. It might be zero, it might be some other value. A particle is just an oscillation in the field. The light that is coming down here and letting you see things, this is an electromagnetic field oscillating. But if you look at it closely enough, the light resolves into individual particles called photons. Your eyes are not good enough to see individual photons unless you are a frog or several other species of animals. Our eyes as human beings, not as good as some other animals. There are animals in nature, including frogs, whose eyes are sensitive enough to see individual photons of light. So what does that mean? Imagine that you're a frog and you have a friend, another frog, who has a lantern. I don't know how this works. This is a thought experiment. And your friend, the frog, is hopping away from you at night, and you see the lantern going off in the distance, and it's getting dimmer as it gets further away. You or I would just see the lantern get dimmer and dimmer and eventually disappear. The frog, with its more sensitive vision, sees the lantern get dimmer and dimmer, and then it stops getting dimmer. Instead, it starts flickering on and off. It's on, and then it goes off, and then it's on, and then it goes off. And the flickering becomes less and less frequent, longer and longer periods of dark scattered with little flashes of light. That's because your eyeballs are picking up individual photons, particles of light. And what quantum mechanics is saying is that really what's going on is there is a wave coming to you and impacting the molecules in your eyeballs, but the process of observation resolves that wave into particles. Not because you're seeing the real essence of it. It's not like a TV screen where you see the pixels. The pixels are what's really made of. What it really is a wave, but quantum mechanics says when you observe these quantum fields, what you see are individual particles. So that's important because back in the 1950s, 1960s, we had discovered these other forces of nature, right? The nuclear forces. We thought we understood gravity and electromagnetism. But the strong and weak nuclear force were puzzling to us. The theoretical physicists of the time were trying to build models of the strong nuclear force and the weak nuclear force. But they immediately hit a puzzle. The puzzle is that just like that lantern moving away from you gets dimmer and dimmer, there's a law, a mathematical relationship that says how quickly the lantern gets dimmer. It's an inverse square law, just like Newton's law of gravity. The square of the distance tells you how dim the light coming from a distant object is. So it turns out that's not an accident. That's a fact that you can trace back to the fact that space itself has 3 dimensions. So you get all the light rays coming out from a source, and they get spread out over a sphere that has 2 dimensions in a 3-dimensional space. So 2 dimensions means you take the area of that sphere, it's the radius squared. There will be a quiz on this afterwards, so I hope you're writing this down. The point is, because there are 3 dimensions in space, individual lines of light or individual lines of force from gravity or from electricity or from magnetism obey an inverse square law. It just seems to be a fact built into the very nature of space-time. And that allows both gravity and electromagnetism to stretch over huge distances. They're relevant for astronomy. They stretch over galactic scales. Whereas the strong and weak nuclear force stretch over the distance of a proton, a very, very, very tiny distance. How can it be? What is going on with those lines of force that make the nuclear forces short range, even though gravity and electromagnetism go off over very large distances? Well, there's a thing that you need to know about the physical world, which is that the principle on which it's based is that it wants to make life as difficult as possible for graduate students in physics. So applying that principle to this question, of course, there is an answer why the strong nuclear force is short range and why the weak nuclear force is short range. And the two answers are utterly different. So more Nobel Prizes for discovering this whole set of ideas. For the strong nuclear force, there's a thing called confinement. There are lines of force, but the lines of force get tangled. They interact with each other. And the answer is much like that lantern has a shutter around it, past which light cannot get. So if your head is very close, if it's inside the shutter, you see a very, very bright lantern. But if you're outside the shutter, you see nothing at all. If your head is inside the proton, you would see very, very strong nuclear forces. Once it's outside the proton, you see nothing at all. The lines of force are confined inside the individual protons, figured out in the early 1970s, and Nobel Prizes given to Gross, Pulitzer, and Wilczek in the 2000s. The weak nuclear force is utterly different. The weak nuclear force says, what if that lantern is walking away from you, but it's a foggy night? There's something in the air that absorbs the light from the lantern. Then once it gets to a certain point, you just can't see it at all because all the light from the lantern is being absorbed. So in the early 1960s, a bunch of physicists said, I bet the weak nuclear force is like that. Peter Higgs was one of these physicists, but he was not the only one, but he had the coolest last name. So he now named this idea the Higgs mechanism. He wasn't even the first, to be honest, but Higgs is a pretty awesome last name. So you have to appreciate exactly how dramatic this idea is. These guys are saying, yes, we know that the world is made of fields, but in addition to the fact that there are fields that you can sort of imagine being at zero, just turned off, there's another field that fills the universe and is not zero anywhere. It's like the fog filling the air that prevents the lines of force from the weak interactions from getting very far. And this obscuring fog should have consequences. That was their prediction. So if you want to think about it one way, this Higgs field, so remember, there's an electron field, there's an electromagnetic field, there's a quark field, a gluon field, etc. But this one, its favorite place to be is at some value that is not zero. For the electromagnetic field, or for the gravitational field, or for the quark field, the lowest energy state is just to have the field sitting at zero. Nothing going on, nothing there. So you can plot that. You can imagine that here is where we are in the universe, some location in space. Here is the value of the field. Here's zero. And you have all these different fields, and they're sort of humming along, oscillating due to quantum uncertainty. But they're all sitting there close to zero. And the idea behind the Higgs mechanism is that the Higgs field is way up there at some non-zero value. This is a very dramatic idea, and back in 1964, it might have seemed extremely speculative. But the thing about fields is you poke them, you make them vibrate, and you make particles. So this idea is speculative, but there's a way to test it. You can look for the particle associated with this field. Just like photons are associated with the electromagnetic field, Higgs bosons are associated with the Higgs field. That's why it's hard to explain the importance of the Higgs boson, because not everyone is as expert in quantum field theory as you guys now are. You need to move beyond the particle description. You need to start talking about fields. Then in 1967, Steven Weinberg and Abdus Salam realized there was a bonus. In addition to this idea that the Higgs field makes the weak interaction short range, it can also be used to give mass to all of those matter particles, the electrons, the quarks, and so forth. So it turns out in the standard model of particle physics, this wonderful theory we have of all the fundamental interactions we've observed so far, without the Higgs, an electron would have zero mass. There's a symmetry of nature that says you can't have any mass for the electron. And Einstein told us years ago that if a particle has no mass, it must be moving at the speed of light. So without the Higgs field, the electron zips along at the speed of light. And you might say, well, all right, I could learn to live with that. No, you couldn't. Here is why. Because you are made of atoms, little nuclei with electrons going around in orbit. Those electrons in the orbit are not moving at the speed of light. If they were massless particles moving at the speed of light, they wouldn't be orbiting. They would just be zipping along. They would not be captured. Without a mass for the electron, there wouldn't be atoms. And without atoms, there wouldn't be molecules. There wouldn't be chemistry. There wouldn't be life. Literally, without the Higgs field, life itself would be impossible. So it is kind of a big deal. With the Higgs field, this electron feels the fact that it is moving through the Higgs field all around it. Every day, if you move your hand, if you walk down the street, you are moving through the Higgs field. Look out into the sky, the sun, the moon, and the stars, they are all moving through the Higgs field. It is affecting the properties of the elementary particles out of which you and I and the sun and the moon and the stars are made. So without the Higgs, we would have no idea how to explain the everyday phenomenological world around us. Obviously, we want to go looking for this beast, so we built something called the Large Hadron Collider. This is the largest, most complicated machine ever built by human beings. It is 27 kilometers around in a ring underneath France and Switzerland at the border outside Geneva. So you can't see the Large Hadron Collider, the LHC as it's called, from an airplane because it's underground. It's 100 meters underground. You could be standing right there in someone's living room or in a pasture, there's a cow, but underneath you, 100 meters, the laws of physics are being discovered. There are a whole bunch of numbers and facts about the LHC which boggle the mind. So here is the Geneva airport, Lake Geneva. This is the CERN site. Atlas, which is one of the major experiments, won the coin toss, and it gets to be next to the main lab. CMS, which is the other main experiment, lost the coin toss. It's over there. 9 billion American dollars is about the cost that the LHC took. It's a lot of money. There's no one denying that. But this is over the course of decades with many dozens of countries participating and adding to it. And there are far more frivolous ways you could spend your $9 billion, I'll put it that way. Thousands of people. What the LHC does is it takes magnets and it accelerates protons to 99.999999% the speed of light. And then it accelerates other protons in the same speed, going the other way, and they smash together and particles fly out. Sometimes people describe particle physics as you smash two watches together, watch what flies out when the watches are smashed, and you try to figure out how watches work on the basis of that. That is a really dumb explanation of how particle physics works, because when you smash particles together, what you're trying to create are not just the particles that are inside. There's no Higgs bosons hiding inside the protons. What you're doing is you're using E equals mc squared, Einstein's equivalence of energy and mass, to make particles that are heavier than the particles you start with. You take protons, you accelerate them close to the speed of light, so the total energy is much more than the energy of a proton at rest. And you create Higgs bosons where there weren't any in the first place. So it's like smashing two Timex watches together and a Rolex pops out. It's very cold inside. There's a lot of cable, blah, blah, blah. It's a very impressive thing, the Large Hadron Collider. It's the kind of thing where no one tells you in graduate school how to build a Large Hadron Collider, because no one knows, because it is the largest machine ever built. So it turns out that, for example, here is a piece of the CMS experiment. This piece of the CMS experiment, when the engineers sat down to design it, they knew that there was a constraint. Namely, that someday it would have to be trundled down the streets of a medieval French city. So it couldn't be wider than a certain size. You build these you bore these holes to lower your magnets down, 100 meters underground. Sometimes when, for example, you're building the hole to put the CMS experiment down, it was a brand new site on the CERN facility. It turns out that you're in the border of Switzerland and France, so of course you're going to hit an ancient Roman ruin. They're all over the place. So all the physicists get kicked out, the archaeologists come in, 6 months, everything stops, you dig up the coins and the pottery and so forth. You eventually kick out the archaeologists, physicists get back to work, you lower your magnets in. September 2008, the LHC turned on for the first time. Champagne corks popped. People celebrated. 10 days later, it exploded. This is the aftermath of an explosion in September 2008. The press release the next day said that we had a leak. It was not a leak. It was the kind of leak that would have killed you had you been sitting next to it. 6 tons of liquid helium were splashed across the floors. The magnets were ripped to shreds and so forth. But there was nobody there because the safety procedures were in place. And it was bad. You know, they've been building the LHC for 2 decades, and it was a crushing psychological blow to have it break within 10 days after it turned on. But to the eternal credit of the people who built, the engineers, the technicians, and the experimenters who designed and built the LHC, nobody got in any way seriously depressed by this. They went to work, they figured out what was wrong, they went to every single magnet around the ring, they fixed it. In November 2009, when it turned on again, it worked like a charm and has been working like a charm ever since, better than ever before. So here are these two experiments. This is the ATLAS experiment. This is the CMS experiment. Remember, you're smashing protons together. Things come out. You want to watch what happens. These are the machines that watch what happens. To get you an idea how big they are, these are people. There's a little person. There's a little person. Neither one of these experiments would fit inside this room. You make many collisions, over 100 million collisions per second. There are over 100 trillion protons moving around the LHC. There's about 1 megabyte of data per collision. So if you kept all of the data that the LHC produced, you would fill up the world's largest database in less than a minute. So you don't. You throw out almost all of the data. You throw away all but one out of every million collisions, and you keep the ones that might look interesting. And the ones that might look interesting look like this. This is a real event. This is real data. This is not a simulation. This is the ATLAS experiment. So one proton beam comes in this way. The other comes in this way. They smash together. A whole bunch of noise comes out. But sometimes interesting particles come out. In this particular case, there's two electrons in the short little lines. These two long lines are two muons coming out back to back. That's a very interesting event because that's the kind of thing that theorists predict that you might expect to come out if you made a Higgs boson. So here's the terrible realization about the Higgs boson. You will never, ever, ever see one. We have not seen one. You make a Higgs boson, but they decay. They're unstable particles. You make a Higgs boson, and it decays in about 1 zeptosecond, which is a really short period of time, 1 zeptosecond. So the LHC detectors are good enough to see things that only last for a millionth of a second, but a zeptosecond is much, much shorter than that. So you will never see the Higgs boson. You will see the thing that the Higgs boson decays into. Sometimes it will decay into 2 electrons and 2 muons. So you do your quantum field theory, and you make a prediction. This pie chart is a prediction for what fraction of the time the Higgs boson will decay into different things. Sometimes quarks, sometimes W bosons, gluons, photons, etc. There's the whole pie chart. The real problem with this is that there's a bunch of other ways to make exactly the same products out of your collision. You will never be able to look at an event like this and say, yes, that was a Higgs boson, because there's many other ways to get exactly that event. What you can do is you can say, if there's a Higgs boson, there will be slightly more events of this type than there would be without a Higgs boson. It's adding to a signal that is already there. So sometimes people say, this is an actual photograph outside the CERN site of haystacks. People say, looking for something like the Higgs boson is like looking for a needle in a haystack. Again, a very dumb analogy. The thing about a needle in a haystack is it might be difficult to find, but you know it when you found it. Looking for the Higgs is like looking for hay in a haystack. If you took that haystack and you piled it up, by length, you would expect to see slightly larger number of stalks of hay at a certain length than at other different lengths. So the whole game is collecting a lot of data, getting good statistics, doing very powerful mathematical analyses, and making as clear as possible whether or not the data you are collecting need a new particle to explain them. And so, when I wrote my book, The Particle at the End of the Universe, it's out there. There is one thing that I tried to put in the book that my publisher balked at, which were these two plots. He said, we can't put those in there. They look science-y. There's like graphs and error bars, and people will be intimidated. And I said, look, we paid $9 billion for these plots. They need to be in the book. And they are in the book. I won that battle. So what are these plots? These are a particular kind of event that you make when you smash these protons together. This is an event where 2 very, very, very high energy photons come out. So these are the energy of the photons in weird particle physics units, billions of electron volts. And this is the number of events. And you see, all right, it's a good number of events at each energy, hundreds or thousands of them. But remember, there are 100 million, whatever. There's a whole buttload of collisions every second. Very few of them look like this. This dashed line is what you expect to see if there were no Higgs boson. Black points are the data. Red curve that is solid is what you expect with the Higgs boson at a mass of 125 billion electron volts. You wouldn't believe it if they didn't put the plot on top, if you just saw the data points, but this is very, very unlikely to not be there, if that makes sense. These data say that without any doubt, these data are not a good fit to that dashed line. You need that bump to fit them. That bump is a new particle of nature. That bump is something that was created when the quarks and the gluons inside the protons smashed together, created a new particle, gave you one more way to make events of this type, so you get a slight enhancement. It is crucially important that ATLAS and CMS both see the same thing in the same place, with the same magnitude. This is how science is done. You're always skeptical if one experiment finds something amazing, but if two, who would love to prove the other guy's wrong, find exactly the same thing, then we can declare victory. We have a new piece of the puzzle of reality, a particle about 126 times the mass of the proton, which we now call the Higgs boson, after many more tests have been done. So what good is it? Is it going to make you a better iPhone or jetpack or cure malaria or anything like that? No, it will not do any of those things. But it is the final piece to the understanding of nature called the standard model of particle physics. It's not the final piece to our understanding of nature, but this particular part of nature we can now say we understand. Sadly, the astronomers keep finding things we don't understand. Here is a picture of dark matter. It's not really a picture. Well, it is a picture. It's not really a photograph with somebody's camera of the dark matter, but this is a map of where dark matter is in a certain part of the universe based on what's called gravitational lensing, the idea that galaxies in the background over here send light through this clumpiness to us over here, and through the bending and twisting of that light, we can reverse engineer how much matter there is and where it is. It turns out there's a lot more matter in the universe than can possibly be accounted for in the standard model of particle physics. So the standard model of particle physics is done, but physics is not. There is most of the universe remaining to be understood. We are very, very hopeful that the LHC will help us. We have many, many models on the table littering the physics journals of what the dark matter might be. In a large proportion of those cases, something will be visible to the LHC when it turns on again. Right now it's on shutdown for 2 years. It's going to come back in 2015 at a higher energy, and we're going to be looking to try to produce the dark matter directly. So where does that leave us? Dark matter is very interesting. Dark energy is also very interesting. The Big Bang, black holes, these are all very interesting things. But the point is, there is a realm of everyday experience. There's the stuff that you and I see with our eyes, hear with our ears, touch with our fingers. Everything in that realm, including what we see in the sky and so forth, is described by the standard model of particle physics. There's no room for new physics that is important to your everyday life that we haven't yet found. That's one of the rules of quantum field theory. If there were new particles, new forces that affected, the motion of the planets, we would be able to detect them, and we haven't. So when it comes to baseballs, tables, viruses, and human beings, the underlying laws of physics are understood. Quarks, electrons, neutrinos, and in the background is lurking that Higgs field. The remaining challenge for discovering new physics is the worlds beyond the everyday, the world of the universe, the world of the dark matter and dark energy, and so forth. And that is what we will be doing. We will instantly go to these other bigger questions. But we should still appreciate the accomplishment here. 2,500 years ago, Democritus and other ancient Greek philosophers started us down the road of particle physics. They said they were the first ones to say that the universe, air and solids, these are not different things. These are all different combinations of elementary particles called atoms. We stole the name atoms for the wrong purposes. What they really meant, Democritus and their friends, were the elementary particles. And we now have part of nature that is understood, the part of our everyday world. We will continue to expand our horizons, but everything that you see in these pictures are made of atoms that we now have a theory that we finally understand how it works after 2,500 years of hard work. That is why it is a big deal. Thank you.
Professor Sean Carroll, ladies and gents. And I don't know about you, but I think the characters in these photos are looking with far more awe and amazement than I've ever seen at a Lady Gaga concert, that's for sure. Now's a great opportunity. We have a microphone, I think, at either side of the stage to ask Professor Sean Carroll any questions that you might have. I did mention before that it's a big opportunity, obviously, because it's very rare that we have someone like Sean Carroll with us in our presence. So I'd encourage you all to come forward, ask a question. There's a couple of people who can guide you down to the microphones. Just while we're doing that, I'll remind you that there is a Twitter handle, Adam M. Shirley. I'm not doing that to promote the ABC or myself. I might say it's the only Twitter handle I think we're using tonight. If you'd rather tweet your questions. To get started, I've actually got a question for you, Sean. Given the huge scientific questions that were at stake here, how many prototypes of the Large Hadron Collider were designed before engineers were certain and it was built?
How many prototypes were designed? None. It's too expensive to design a prototype. Of course, every little piece of the Large Hadron Collider had a prototype for it. And one of the amazing things about an experiment of this magnitude is the scope, full stop, but also the international nature of it. More than one physicist, when I was writing the book, said unprompted, if only the United Nations worked as well as CERN did, there would be peace on Earth. And if you look at this picture of the Atlas experiment, there's 100 countries represented on the Atlas experiment. The collaboration that does the work is 3,000 people. Every time they write a paper, there are 3,000 authors to every paper they write. But you look at two components right next to each other, and one was made in Argentina, and the other one was made in China, and the one next to it was made in Russia, and it all works together seamlessly.
In some ways then, does it amaze you and countless scientists that it was such a smoothly run operation? Or was that because CERN and the whole program that was involved was so well designed in the first place and everyone was on the same page?
Well, it amazed me in the sense that, I was a tourist in experimental particle physics. I do theoretical particle physics. My occupational hazards are, caffeine overdose and repetitive stress injuries. But so I went into writing the book already very impressed with the work that has been done by experimental particle physicists, but came out enormously more impressed because they're very, very competitive, these people. 3,000 people in a collaboration, so you're fighting against the other collaborations, you're jostling for position within your collaboration, and you're trying to fight nature, who is stubborn in giving up secrets. But it's all about getting the right answer. You can't cheat, right? You can't fudge the data and think it'll be okay because there's another experiment that's going to find the right answer. You need to get there first, but only if you get there right. And their absolute dedication, again, for no immediate economic impact. It's just because they want to know how the world works, just because they're curious, just because they retained that sort of 6-year-old sense of awe and wonder about how stuff works that forces them to work as hard as possible to get it right.
I have a couple of questions from the audience, I think. We've got to ask her on this side. Please, go for it.
First of all, can I thank you for a brilliant talk, content
Yes,
and presentation. Magnificent.
Thank you.
Could I just ask, though, what's the connection between a Higgs boson and mass? Is there a one-liner for that?
Appendix B? It's a very good question, and the short answer is no, there is not a one-liner. There's a 6-liner. When it came to the point where we could finally begin to understand the weak interactions of particle physics, there was this remarkable fact called parity violation. If you do an experiment and it involves the weak interactions, and you imagine doing the same experiment in a mirror, so right and left are interchanged, physics says you get a different answer. And this has been experimentally verified. Again, Nobel Prizes were given out. So the theorists sat down to try to understand how to build a theory that would treat right-handed particles and left-handed particles differently. They thought of a way to do that at the cost of saying, now we don't know how to give particles mass anymore. If it weren't for the fact that nature treats particles spinning clockwise and particles spinning counterclockwise differently, then giving mass to particles would be no problem. But that extra weirdness, that chirality, that handedness of nature, mathematically implies that everything zips along at the speed of light, because giving mass means that you need to connect particles spinning clockwise and particles spinning counterclockwise. The Higgs boson filling empty space provides that connection. How's that?
Right, thanks.
Good, that's the right
Thanks a lot
answer.
for asking a question. We have someone over here as well.
Hi, similar sort of question. My understanding is the Higgs field pervades the entire universe and it gives things the quality of mass. But we also have the space-time continuum pervading the entire universe, which is warped and its geometry is changed by the presence of mass. So is there some connection between the Higgs field and the space-time continuum?
Yeah, that's a very good question. There's two things that mass does. So the short answer, there is a one-line answer to your question, which is no. But it's a subtle way in which it happens. There's two places in physics where the idea of mass shows up. One is what is called inertial mass. It's basically the resistance you feel when you push something. When you push a big car, it takes effort to get it going. Push a little toy car, it's a lot easier because the mass is smaller. There's another thing called gravitational mass. The Earth causes gravity in proportion to how much mass it has, or the sun or the planets or whatever. It turns out, ever since Galileo and Newton, we've known that these two things, the inertial mass, resistance to being pushed, the gravitational mass, the thing that causes gravity, are equal. And Einstein explained how that could be true and why that should be true in his general theory of relativity. But the Higgs gives inertial mass to things. So even if there was no such thing as gravity, the Higgs would still be giving mass to elementary particles. It does turn out that the gravitational field caused by those particles is now different because they have mass. Even if they didn't have mass, they would still cause gravity because everything causes gravity. Photons cause gravity even though they're massless. So Higgs has nothing directly to do with gravity. It's just that Higgs has to do with mass and mass has to do with gravity.
Fantastic. Over to my left as well. Go for it.
Thank you so much. That was so much better than studying for my exam tomorrow. I was wondering, you mentioned at the start of your speech that there was a lot of times in history that we thought we were pretty much done, but now we know that we are. So I'm wondering how we know now that we are done.
How we know that we are?
Yeah, how we know that we're done finding out everything and we're not going to open up quarks and
Right.
new things.
Very good. So I need to be very, very, very precise in this statement. We are not done. We do not have a full understanding of the universe. What quantum field theory lets us do is divide the universe into chunks. Here are the protons and electrons and photons interacting with each other. There's the dark matter particles, and they interact with each other in their own way, and so forth. And what we can say is the part of nature that is here in this room, you and me and the floor and so forth, that part we understand the underlying physics for. And the reason why we know that is because quantum field theory says, all right, if there's something we're missing, it's going to be a field. Tell me what particles that field interacts with and how strongly it interacts. And then I can make it. If I have a field that interacts with a proton, I shake the proton and that field starts shaking. So we know that any fields that we're missing so far must be either very, very short range, much shorter than the size of a proton and therefore not really relevant to chemistry, molecules, or life, or very, very weakly interacting, like the dark matter. Dark matter is just going through your body right now, but it just doesn't interact with you. So the part of nature that is here in this room is understood, that I cannot in any way tell you how much of nature that is, right? I mean, we know that dark matter and dark energy are most of the universe by mass, but who knows how complicated they are? Who knows how many tens or dozens or hundreds or millions of particles there are left to be discovered?
We've got someone else coming down. I'm going to sneak in just quickly as well, just as a follow-up to that previous question. When will we know? When will we know that we're close to being done? Or is that time ever ongoing, I suppose?
Yeah, I think it's pretty ongoing in the sense that it would be very difficult to know that we were absolutely done. I mean, the nice thing about quantum field theory is it says that if you imagine a new part of physics that is strong enough to do blah, 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 then we know whether we found it or not. But there could always be other particles that are just too weakly interacting to notice, or just not enough of them to be created, or too heavy to make in the lab. It would really be very difficult to know that we were finally done. So there are plenty of incidents in history where physicists have said, we're almost done. Don't ever believe them when they say they're almost done. Believe them when they say, we understand this. Don't believe them when they say, we understand everything.
First of all, thank you for helping with the question I have due tomorrow on the range of the strong nuclear force.
Good.
And secondly, showed us your $9 billion plots that proved that showed we had found something that weighed 126 gigaelectron volts. Is there any more that's been shown to show that that actually is the Higgs, or is it just the fact that the standard model doesn't leave anything else for us to find and we found something, so it must be the Higgs?
Now, that's a very good question. How do we know that that bump is the Higgs? It's something. It's some new particle. So it turns out we have a lot of information. Not only did you make two photons, but you know sort of where they came out, what angles they come out at. You know how frequently they come out. Remember, you had the pie chart. You don't only make photons, sometimes you make other kinds of particles, so you search for those decays as well. And now you have about half a dozen different little tests that you're doing. If this new particle is the Higgs boson, it will do this and this and this and this. And as of just a few weeks ago, the physicist said, yes, it does exactly what the Higgs boson is supposed to do. To everyone's great disappointment, in some sense, it's always more fun as a physicist to be surprised, to say, well, we thought we were getting the Higgs boson. Instead, we get 8 Higgs bosons. That would be awesome. And it might even be plausible. There's very respectable theories that have multiple Higgs bosons in them. So this is certainly a very Higgs boson-like particle, but we're not stopping our tests of how Higgs-like it really is.
Some bonus marks for your exam tomorrow there, by the sound
Yeah.
of it. We're fast running out of time. I think we've got time for one more person to jump in if they so choose. Oh, and I think it's who better to ask a final question than Charlie Lineweaver, ladies and gents.
Getting ringers in here.
I just have a couple of questions. One is, what is a zeptosecond? Is that 10 to the minus 18 or something?
It's very small, very short.
Okay.
You can Google that. What are you standing up and asking me this question?
No,
I think it's 10 to the minus 21 seconds, but you should
sorry.
Google it.
Okay, one thing is that you had a very nice explanation for the strong nuclear force and gravity, and I think, I like to think of planets are held together by gravity, and atoms are held together by electromagnetism, and protons are held together by the strong force. But I'm wondering, what does the weak force hold together? Is there any structure that I can say, hey, that's held together because there is a weak force?
No.
No, so it's only repulsive or something?
It's weak.
Yeah, it's weak. How about a weak object somewhere? There's nothing. It's just repulsive and then decays.
There are no bound states in the standard model due to the weak force.
Doesn't lift any arm weights then, clearly.
I mean, in the standard model, the only particles that feel the weak force and not some stronger force are neutrinos. And their mass is so small, they just don't bind.
It's been a fantastic evening, I'm sure you'll all agree. We're very fortunate, as I said at the very beginning, to have people like Professor Sean Carroll, Professor Brian Schmidt, Charlie Lineweaver all in the audience. I feel like I'm far better educated, mind you. It'll probably go out this very hollow head of mine. Most of it will anyway. Sean Carroll, fantastic to have you in Australia and in Canberra. Thank you so much for coming along tonight.
Thank you very, very much.
A big thank you to the Australian National University, obviously, for making this venue available for such a great event. And of course, to our Nobel Laureate, Professor Brian Schmidt, for making it all happen in the first place. Airfare's never looked so well worthwhile.